And this is the holy grail of fusion research. Now, the rest of it becomes, you could say it's engineering. It's stuff that we actually have not really been focused on.
This is Energy Cast, and I'm Jay Downhauer. Today we're talking about a historic moment for fusion power. This episode comes a month after what has been called one of the greatest discoveries of the 21st century. In December, it was reported that our guest today produced more energy from nuclear fusion than was used for the reaction. This net positive phenomenon is called ignition, and until then it was only theoretically possible. But this announcement now means that fusion efforts across the public and private sector can now say it's possible. And from what I've heard from some of the companies I've profiled in the past, investors are calling. Still, one of the truisms of fusion remains, and that is that this technology takes time. Some reports shortly after the cheerful celebration pointed out that the reaction was not net positive in that it took more energy to prime the lasers involved. My guest says that they were very transparent from the beginning. What mattered most was that the energy at the BB-sized point at the center of 192 converging lasers made more energy. Everything else, as she puts it, is engineering. I make the point that if you go far back enough in the energy production process, you'll probably reach a point where it takes a lot of energy to produce the plant that is making the energy. Take wind turbines, for instance. But what is undeniable is that this fusion first is one of many we can expect to see in the near future. My guest today is Dr. Tammy Ma, lead for the Inertial Fusion Energy Initiative at Lawrence Livermore National Laboratory in California. Tammy leads the efforts at the National Ignition Facility, or NIF as they call it. This is the size of a football stadium, where lasers I mentioned focus on a container called a holrum, which houses a BB made of frozen deuterium and tritium. Zap it with enough heat and pressure and you fuse these hydrogen isotopes into helium, with neutrons creating the energy. We bring this up a few times. NIF is not a power plant. Construction began a year after the passage of the Comprehensive Nuclear Test Ban Treaty in 1996. Since it was completed in 2009, most of the NIF tests simulate the effects of nuclear weapons without the mess of underground testing. It turns out the NIF was ideal for testing inertial confinement fusion. NIF announced they were close to net positive ignition in mid-2021. In December 2022, they announced ignition with a ratio of about 1.5. Tammy and I covered the gamut of what the most recent announcement means for the industry. What does it mean for fusion using magnets instead of lasers like this one does? Does this breakthrough mean anything to them? Also, the NIF produced energy using one shot, as they called it. What would multiple shots per second needed to sustain a fusion power plant look like? I hope you enjoy my conversation with Tammy Ma. We're here with Dr. Tammy Ma, lead of the Inertial Fusion Energy Initiative for Lawrence Livermore National Laboratory. And Tammy, last month it was announced that your team at Lawrence Livermore achieved ignition, producing more energy from fusion power than it took to create it. This has been called, quote, one of the most impressive scientific feats of the 21st century, not to oversell it. So how has your life been over the last month?
Here at Livermore, our team has just been celebrating. It has been wonderful to be a part of this enormous group of people building on decades of work, and to finally see fusion ignition be realized has been really exciting. As you can imagine, we're getting a lot of media requests and requests for seminars and talks. So it's been really busy, but you can't ask for anything more as a scientist, right? That's what you aim for in your career.
Certainly. I appreciate you honoring this media request, but I'll just tell folks it depends on who you know. So,
sure.
But I was hoping you could help my listeners understand what ignition means, as opposed to concepts like plasma or just fusion in general. For instance, can there be ignition and plasma that isn't net positive?
Absolutely. So on the National Ignition Facility, what we actually do is fusion experiments. All of our experiments where we use deuterium, tritium fuel, or even deuterium deuterium fuel, we are already generating fusions. So we are getting those atoms to fuse. Now, what ignition means is that for the first time, we were able to actually get more energy out than we put in with the lasers. That is our definition of ignition, i.e. scientific net energy gain.
What about when we talk about plasma, right? What are we talking about there? Is this plasma as well?
We are always generating plasmas. A plasma is just an ionized gas, essentially, right? So you put enough energy into a gas, you can liberate the electrons off and you make an ion. And then it very often glows or there's special properties. In our fluorescent light bulbs, there is a plasma. There's plasma kind of naturally occurring all over space. It is actually the most ubiquitous state of matter in the universe, believe it or not. It's just here on Earth, we're more familiar with solid gas or liquid. What we're getting at is burning plasma, which we were also able to achieve on the NIF in the past couple of years. And a burning plasma is kind of equivalent to you lighting a match and that flame growing. That is burning plasma. And it is an important step for us in the fusion reaction before you can achieve full ignition, the energy gain out of the target. And so there's been quite a few experiments now on the NIF that we can regularly achieve this kind of burning, almost to self-sustaining plasma, essentially, is what it means.
It said that a net positive or break-even reaction has never happened before. And this is across all the different fusion technologies, I'm assuming. What helped make it work for your team?
It's absolutely correct. This is the first time in a laboratory in a controlled setting that we've been able to generate net positive, more energy out than we put in via fusion reactions. And this is the holy grail of fusion research, really. There's all kinds of other technical work that needs to get done, engineering and supporting technologies, but this is the very first step you absolutely need to demonstrate in order to show that fusion might be viable. What did our team do? Again, we're building on decades of research, right? So, Livermore has had a series of bigger and bigger lasers to try to be able to have a driver that is big enough to actually make sustained fusion happen. Here on the NIF, over the past couple of years, we've really gotten a better understanding of the physics and what our sensitivities are to different small perturbations. What I mean by that is we have to drive the implosion so symmetric so that we can very efficiently convert this kinetic energy of compression to heat and not waste energy there. And we have to understand how to couple a lot of the laser energy into the whole ROM. If laser energy bounces out or gets absorbed in the plasma through instabilities, again, you are wasting energy. And then there's a few other things that we saw that we were very sensitive to in our implosions, and we've learned how to control them. So there's definitely that. And then we've also been continuously working to improve the laser. It is already the largest, most energetic laser in the world. And it's a beautiful, beautiful feat of engineering. But even then, right, you can always continue to improve the technology, make the pointing of the lasers a little more precise, exactly the delivery between those 192 laser beams. You want them to match exactly, and each laser to give you exactly the energy you want at a certain time. On this most recent shot that got us to ignition, the big improvement was that we were able to up the laser energy by 7% over previous experiments, and that seemed to give us just that extra push that we needed.
The announcement was about mid-December, and the reaction, the day it actually happened, was December 5th of 2022, just in case they listen to this episode later. The last big public announcement from Lawrence Livermore came in August of 2021 that you'd achieved about 70%. So over a year had passed. So help us understand, how often are you performing these tests? Do they take months to set up? Are you doing them continuously or not?
Well, the facility itself does run 24/7, but we do a wide variety of experiments. There's astrophysics experiments, what we call high energy density experiments, and then also ignition experiments or ignition attempts in between as well. Over the past year, we did a number of shots where we tried to repeat what we had done in August. Now, because the targets that we were working with were not quite as good, quite as perfect as the August shot, our performance was still very, very good. We achieved burning plasma, alpha heating, definitely really good fusions going on, but not as high a gain, not to that 70%. We did a series where we did try to repeat, and we wanted to understand the sensitivities to perturbations there over the past year. And then we made small changes also to geometries, the laser, and then that's what pushed us in 2022 December for ignition.
I think it said the actual ignition occurred at like 1 a.m. That seems a little unusual, right?
For us, again, because we're a facility that runs 24/7, we want to try to make the best use of our facility as possible. So as soon as one experiment's done, we start the next one, and we try to execute them as quickly as possible so that we can get the most out of this oversubscribed facility as we can. Everybody wants to be on the NIF, so we want to serve our customers and science as well as possible.
Yeah, I think the press release said that at the time you were at an airport. Is that right?
I was. So I was not directly involved in this particular shot. And so I was not one of the ones that stayed up overnight, was watching the data as it came in. But I did get a call the next morning from one of my colleagues, my boss here at Livermore, kind of whispering the news because, we want to be very cautious. We're excited. We knew it was a big shot. We definitely wanted to verify the numbers and wait for all the data to actually come in and be analyzed and put error bars on that to make sure we were sure before we made the big media announcement.
It was kind of maybe indicated that the news got leaked. I think there were some initial reports maybe in Financial Times, and then an official announcement with Jennifer Granholm and all that a few days later.
That's right. So we have collaborators all over the world, and many that work with us on these ignition experiments. And word got out that it was a big shot. And I think the excitement in the fusion community was so great, it boiled over, and in some cases got out to the press as well. Of course, as you know from that Financial Times piece, they did not report quite the right numbers for gain or energy out. And that's because it was at that point still rumors. But yeah.
Yeah. That's what it sounded like. It sounded like it was from a place of enthusiasm, not anything other than that. It was reported, just for the listeners here, you created 3.15 megajoules out of 2.05 last month. It's weird how you measure these things, right? So if you just do a search of 3.15 megajoules, it works out to less than a kilowatt hour of energy. But it's our understanding that these reactions happen in like a split second. So obviously compounded out over an hour, that would be a very large megawatt hour number. How much power would that be continuously?
I have not done that calculation, so I actually don't know. You're exactly right. If we were to turn this into a fusion power plant, you would have to repeat the reaction many times per second. So that could be the integrated total energy coming out to be great enough that you could run the power plant and feed out to the grid.
Okay, so let's talk about what that would look like continuously. And we got to also point out that Lawrence Livermore, I think you brought this up, Tammy, is not a power plant. It's used for a lot of different kinds of reactions. I think we'll get into that in a little bit. But in a sustained reaction, what do you picture changing? Would the pellets be bigger than, I think it was described as being about the size of a BB? Would you have more powerful lasers? Do the pellets continue to be added just one after the other? What would a sustained power plant using this kind of technology for fusion entail?
Right. So you are exactly right, Jay. The NIF is a scientific demonstration facility. We do shots once every 4 to 8 hours or so. In an inertial fusion energy power plant, you would have to repeat the reaction something like 10 times a second. And the gain coming out of the target would have to be significantly greater than what we've demonstrated so far. So instead of a gain of 1.5, conceivably a gain of 10 or 100. And it depends on your overall system, right? How you pull it all together and the efficiencies of those different systems. If you're repeating this reaction 10 times a second, the idea is you could conceive of something that is similar in size and scale to the NIF today. Let's start there. You would be dropping in a target 10 times a second. Your lasers would track that target as it's coming in, engage, and then shoot right when it got to the center. Target size-wise, again, it depends a little bit on the design and where we go from here, but it'll be similar scale. So the capsule, like you said, is 2 millimeters currently. It would be on the order of millimeter size, somewhere around there. Total amount of laser energy, it really, again, depends on your design, but it would range probably from a megajoule up. If you wanted to go above what we have on the NIF right now, it just makes your overall design more robust as well. But then, of course, you have to feed those lasers, so it takes a little more energy. So it's all a balance of plant in all different areas. And then you have the heat extraction system. So you would, in a power plant, you would fire on the target would implode, you get the fusion reactions coming out. Most of the energy would be contained within neutrons, and those neutrons would get absorbed in some kind of wall where you would then convert that energy into heat. You have a heat extraction system. You would need a tritium recycling system, and then that heat would most likely be turned into steam. You use your steam to run turbines, and then it looks like a conventional power plant.
That's interesting. I never knew that tritium was recycled in the reaction. Part of it you can recover?
Yeah, you can absolutely. You recover and you recycle it. That's just to keep the overall inventory down as well. You don't want too much tritium in the system because it's a very valuable resource. There's been article in the popular press that, oh, we're very low on tritium. How is this going to work? One of the benefits of an inertial fusion system is the overall inventory you need for tritium is actually pretty low because these targets are tiny. But of course, you still want to recover and recycle that tritium if you can, that doesn't get used.
Okay. Just for me to understand. So is this tritium that doesn't fuse into helium?
Yeah, exactly. In a magnetic fusion system, you would only burn about 1% of the tritium. So there's a lot of, you could call it unused tritium that you would want to recycle. For inertial fusion, if it's efficient, you should be burning something close to 30%. So you use up a lot more of the tritium. It's more efficient that way. But then you still have 70% that is unburnt that you could recover and recycle.
Okay. Let's talk about the lasers real quick. Do the lasers have to be primed, or if it was continuous firing, how much energy is consumed with the lasers? How are we supposed to think about that?
No laser is 100% efficient, right? Because what you're doing is you're drawing electricity from the walls and you're using that to pump your laser media. And that's how you generate a laser, essentially. Because a laser is coherent, meaning all of the light is exactly the same color. What you need to do is there's laser media that you pump, and then the laser starts out as a little seed, so a tiny packet of photons. It passes through this media, gets amplified. It increases your little packet of photons, all of one color. And that's how you generate very energetic lasers. For us on the NIF, drawing from the wall takes about 320, a little bit more megajoules. 322 is the number that we quote. That energy gets drawn from the wall, gets stored in huge capacitor banks so that it can all get released to the laser. And it's all a compression over time is the way to think about it. And eventually space as well. You're taking energy from the wall, storing it so that you can release it in shorter and shorter timeframes. And that's how we get the huge powers on the NIF. It's about $14 in electricity per shot. Yeah. So it's not a huge amount of energy per se, but it's high energy density because we're going to condense it all down.
Yeah. About the lasers, I wanted to address an article in The Economist I read over Christmas break. It's a little bit confusing, but it seems like they're trying to say that the reaction that you guys achieved wasn't net positive in that some of the energy needed to fuel the lasers wasn't part of the input equation. Help us understand that. Is there a misunderstanding there? What exactly are we measuring as energy in?
Sure. I would say there is a little bit of a misunderstanding. We've been completely transparent about the energy efficiencies at each step, and we're not trying to claim anything that is crazy. What we have demonstrated is what we're calling scientific net energy gain. The big scientific challenge is just having a fusion reaction where you get more energy out, then you deliver to the target, right? The scientific package is what happens at the target. So what we do is we measure the laser energy that is incident on that target. There are all kinds of inefficiencies there in absorption and conversion. In our case, laser energy to X-rays, X-rays to this implosion to heat, and then what comes out. So what we have demonstrated is, again, more energy out of the entire target reaction than we put in with the lasers. And that is already the first time that has been demonstrated anytime in fusion research. Now, the rest of it becomes, you could say it's engineering. It's stuff that we actually have not really been focused on. Like our director, Kim Boudil, said at the press conference, you can't plug NIF into the grid. We're not claiming that we can generate such an efficient reaction that it is something that you can actually feed out and use yet. But this was biggest scientific challenge. And there are many pathways now where we can get to higher target gains, but then we can also improve the efficiency of the system itself. There are new laser architectures today that are far more efficient with wall plug efficiency. There's definitely places in a full system, like we just described for a power plant, where each of those efficiency numbers do matter.
Yeah, I tried to explain to my wife what was going on here. And I was like, I think this is the same thing as the first person who ever ran a 4-minute mile or the first person who ever dunked a basketball. It's like up until then, you didn't know if it was possible. And then it was done. And now it's just table stakes, right? It's just, let's improve the efficiency of the laser. Let's prove this. But now we've proven that it's theoretically possible. And I think that's what we're after here.
Exactly. Yeah. And the analogy you keep hearing in the press is the Wright brothers flight, right? They demonstrated that human flight is possible, but there were still many, many steps before the commercial traveler, we could hop on a plane and actually get somewhere, right? Where we needed to go.
Yeah. At some point, when you start talking about this game about efficiency in versus efficiency out, what if you did that for a wind turbine, and all the energy it takes to mine and build? And I mean, where do you stop? Right. And so I think you kind of get to that point where, okay, we're just initially talking about you're putting energy in, you're putting energy out. So I appreciate you taking a little time to explain that to folks. The lab at Lawrence Livermore uses a fusion technology called inertial confinement. You're using a laser and a tritium-deuterium reaction. I've also profiled technologies that use magnets like the tokamak design. I know TAE uses lasers. Zap Energy is using something else, you name it. How do you think this discovery here helps with these other fusion technologies, even the ones that aren't using lasers, like the ones that are using magnets?
Yeah, that's a great question. I mean, there are a lot of commonalities amongst these different approaches. The game in fusion is you have to achieve what we call Lawson's criterion, which means the density of your plasma times the temperature of your plasma times how long you can actually hold it together long enough to fuse. In magnetic fusion, they use magnets to try to confine the plasma for a very long time, and you can have much lower densities, still pretty hot, but lower densities holding for a long time. For us, we are called inertial confinement because we are relying on the inertia of the target itself to hold itself together. So we have to get very dense, very hot, and because of that, we can only hold it together for very short time scales. But in either case, for all of these different fusion approaches, it's a trade-off between those three different parameters. And that's why there's all these different drivers you hear about too, to try to make fusion happen. And so what we've learned here is a validation that it works. And we all, in some sense, use a body of experimental data that feeds into our simulation codes as well to better understand what's going on. And so this is a very important validation that, our codes aren't crazy, right? We've built it up over the decades. We know they're not crazy anyway, but this is a wonderful data point to add on there. And then similarly, the physics of burning plasmas, the physics of alpha particles, which we haven't really talked about, the physics of confinement, all of those things, there's commonalities between these different approaches, and we do learn from each other. So this, I think, is a big milestone for all of fusion, not just inertial.
Sure. And one of the things I've heard from a few of these companies is the investors are, those phones are ringing,
Absolutely,
and
yes.
More so. And I think that's the big thing too, is now it's a smarter bet, I think, for a lot of the money folks.
And that's great for the field, for all of us. Yes.
The announcement last month said this could also aid in our national defense. And we kind of danced around this, but in addition to fusion power, the National Ignition Facility stays pretty busy. It was originally developed for our stockpile stewardship program. What does that mean? What originally has NIF been there to do?
The National Ignition Facility helps provide for us experimental insights and data for our science-based stockpile stewardship program. And what that means is on the NIF, we are the only laboratory on Earth where we can achieve the conditions, temperatures, densities, pressures similar to what we might have inside a nuclear weapon, but at a very, very small scale. You've seen our targets, right? They're minuscule. So again, we're not building new weapons at all. We can study at a very micro scale, very precisely some of the similar physics. We use the physics, the experimental data that we get to, again, validate the simulation codes. And these are the same codes we use to make sure that our stockpile stays safe, secure, and reliable. In addition, the NIF is this exquisite tool that we use to train what we call our stockpile stewards. So like myself and my colleagues here at Livermore and across the complex to understand the similar physics and to do these very exquisite experiments. And it is just a deterrent alone to demonstrate to our adversaries in the outside world that we have this capability. We know what we're doing. We understand the physics of our weapons, even though they are buried underground and we no longer have underground nuclear testing. So how do we make sure they're still safe and reliable? It's through this knowledge base that we contain.
Yeah, it sounds a lot less disruptive.
Yeah, no, exactly. Yeah. Exactly. Yeah.
And then finally, in the press conference, and you've talked about this today, your team says there's still a way to go. So what's the next goal now that the celebration?
Yeah, absolutely. We're still getting paid. We're still working. So on the stockpile stewardship side, we very much still need to continue push to higher gains and essentially higher neutron yields. The higher yields that we have, the more flexibility and agility we have in the types of experiments that we can do. This also opens up a pathway to inertial fusion energy. So now we've done that little first step of showing that we can get more energy out than we put in. Now, how do we get much more energy then we put in, and then in parallel, developing all of those supporting technologies we'll need to turn this into a viable fusion power plant.
Fantastic. All right, Tammy Ma, Lawrence Livermore, thank you so much for your time.
Thank you so much, Jay. It's a pleasure.
That was Dr. Tammy Ma, lead for the Inertial Fusion Energy Initiative at Lawrence Livermore National Laboratory in California. Tammy mentioned that the NIF stays busy around the clock. In addition to supporting national security and pursuing fusion ignition, NIF executes approximately 400 experiments per year for users, including researchers from national laboratories, academia, and other national and international collaborators. I want to thank Tammy for her time, as well as Brianna Bishop at Lawrence Livermore and Steve Dean, my guest from episode 20, who knows everyone who's anyone in nuclear fusion. Tammy told me Steve was there at the big press conference last month, no doubt as a VIP. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram at HostEnergy and Twitter at HostEnergyCast. All guests are sent the wrong completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 157. Be sure to join us next week when we learn how one small modular reactor developer is cutting the red tape. Until then, I'm Jay Downhauer. We'll see you next time.